3. Olá, gente. Bem-vindos ao novo seminário da DRCC. Hoje temos o William Badgett, que ele se formou na Universidade de Chicago. Depois fiz um mestrado e um doutorado em Ann Arbor, na Universidade de Michigan, em Ann Arbor. E depois participou, eu tentei lembrar, mas praticamente, se você conhece um experimento de física de partículas nos últimos 20 anos, provavelmente ele participou nele, da era a Minas, a CMS, há muitos. Agora ele é um research scientist na Fermilab e vai falar sobre o Short Baseline Neutrino Detector.
I understood a little tiny bit about it. I think my name and Ann Arbor and short baseline neutrino experiment. But I think you stole my signal. So before I get started, I'd like to apologize in advance. I just flew in this morning. Poor planning on my part. Notice I was giving a talk right on the day I was arriving after 12 hours of sleep deprivation. Did I say anything weird? A little bit about me. I saw my picture here. Oh no, it's a little embarrassing. So, detector work history, I've been working on a whole series of particle experiments. Some of them show my age, for example, the Sudan 2 nucleon decay experiment at the SBND laboratory in Berlin, Minnesota, the SEC, which I found most young people don't know. How many people have heard of the SEC? Or the SSC collider? Okay, you don't count. Yeah! See, nobody. So we need to do better teaching history of particles. It could have been a great machine, but it lost on me. I was in the CDF. It's more likely for you to have heard of, but also sort of rare for young people. This is the collider detector of Fermilab. This is one of the two main general purpose detectors in the temperature. Which until, what was it, 2000, the LRC started in 2010. They took over the mantle of highest energy collider. Worked on a CMS also in two different guises, one as a postdoc, one as a staff at Fermilab. I sort of segued into neutrino experiments, starting with the Minos Plus experiment. Lariat. Anyone heard of Lariat? Nope. Oh, this is a little tiny experiment with the Liquid Argon TPC. Test beam. We called it the little detector of Baker. And it was slightly ICARUS and SBND, which is the main topic for conversation today. Let's see, my most recent work, this will be a detector-heavy talk. Obviously, SBND is still being prepared in the Booster Neutrino Beam at Fermilab, so there won't be any physics results. Recently, my concentration has been on detectors, specifically things like data acquisition, trigger controls, and computing. I don't really get into theory at all. Here's my thesis back in 1994. This is the W and Z cross sections decaying into muons. So from that, you can extract the width of the W. All right, this is a bit of a spoiler. I'll advance to the end. Normally, I might show this at the end. Recently, we've had delightful news. First of all, it's me in the far left. Behind me is the SBND detector, the TPC, and the light gun covered in amber plastic. This is to prevent we have a wavelength shifting chemical called TTB coated on PMTs, and it will be degraded with exposure to visible light and UV light. Good news here is that 2 weeks ago, it was 2 weeks ago, the SBND detector was inserted into its cryostat. see the cryostat just on the edge there, and it's actually had to be rotated. One of the things you see here, this is the light detection system. This consists of 120 traditional photomultiplier tubes and also very nice new technology which was invented, I think it was invented here, right? The Arapucas, called the Arapucas, which is, I guess, understand as an animal trap or something.
No, he was doing the original before.
No, I mean the original word.
Ah, yes. So,
So,
yes, Arapuca is a native Brazilian word that is trap for bees.
so I will not go into details there because I don't want to spoil your thunder. On the side here, we have what's called a field cage, and this end here is called the anode, and in the middle there's a cathode at very high voltage. I'll get into the details later. And it was remarkable. Engineering tolerances are very, very tight here. Everything is very tight about the SBND detector, and of course fits very nicely into the current set. And I'd like to show you an alumna of UNICAMP, Monica Nunez. Does everyone know her? I think so. Good. Nicola McConkie and Anna Shoecraft from the U.S.A. They were all three critical to the whole process, which this thing took months of planning. And worked out, went like clockwork. Milestones in the near future, cryogenics operations in July, cool down starts September 19th roughly. I'll go over all these concepts during the later part of the talk. I told you this was a spoiler, so I'll have a 4-minute parse point talk, the overview of Fermilab particle beams, including the SBND beam, Booster Neutrino Beam, introduction to the short baseline neutrino physics program, details on the SBND detector, and this is what I've been working on the last few years, how the data acquisition, timing, triggering work at SBND, with contributions from people in this room. So if I say something wrong, tell me. At heart, the Fermilab accelerator complex is a high energy proton factory. Historically, it has been the Booster. It was one of the earliest machines, accelerators here at there at Fermilab. Accelerate protons up to 8 GeV. It's fed by a LINAC main injector. These protons go into the main injector, which raises their energy to 120 GeV. This is a critical part of the temperature to get more luminosity and more antiprotons. If you're interested in temperature, ask me more later. The temperature finally was by far Fermilab's highest energy accelerator, almost 1 TeV per beam. It's used at proton-antiproton collider mode. And it was since eclipsed by the LHC, and long live the king. Wait, no, it's called The King is Dead, Long Live the King. So, once protons, you can have a whole panoply of other particles, a whole alphabet soup. The physics beams, the primary protons from the main injector, it's what's called a switchyard. It's sort of like measuring the train tracks. Show a picture in a moment, where you shoot protons here, there, and everywhere. So from these primary protons, you can have secondary and tertiary beam in the injector. Switchyard, you have electrons, muons, pions, neutrinos, kaons. There's a P and a P bar. Protons and antiprotons. There's a muon beam for the G-2 experiment, and eventually, at some point soon in the near future, it will go over, switch over to the U2E. So Again, ask me if you want to learn more about these. Just a brief overview. The Neutrino Beam and its complementary BNB Booster Beam. Those are two U.S.A. neutrino beams. UME has long been used by the Venus experiment. And now the NOVA experiment is the primary user of that beam, looking for the one of the main things they're looking for is the CP violating element, delta CP of the neutrino mixing matrix. Remarkable thing about UME, you can switch between neutrinos and antineutrinos. Mentioned why later, how. And Booster Neutrino Beam is for the SBND. SBN group. Okay, I like this picture, but it has a lot of information. Right. So we start off with LINAC. It's very cool looking thing. I think that, in fact, the LINAC came before the booster, so it's the oldest accelerator at the lab. They start off as H- ions. By the time they get to the booster, they're H+ ions, simply protons. From the booster, they are raised at HEV and then injected into the main injector, and that raises them. That ramps up the energy to 120 keV. Here is the tevatron I mentioned. This was the almost 2 keV center of mass energy collider up until 2011. This is the switch yard. You can see it looks like a forking racetrack. So you want many protons, you can get them by switching them down. Switch yard. Okay, so this is how we create neutrino beams at Fermilab. The basic input is always protons. In this case, at the booster neutrino beam, it's AGV, incident protons. They hit a beryllium target approximately there, and basically you're creating a more particles but brute force. You just smash protons into a target and see what comes out. Vast majority of particles that come out are pions. There's a magnet in the shape of a horn here, and you can select the charge of the pions, or plus or minus, and you can sweep the ones that you don't want out of the way. Now, boosters never run antineutrino loop, but the UME beam has. So the next part is the decay pipe here. Basically, you let the pions decay into a muon and a muon neutrino. And you want to get rid of the muons. They're minimum ionizing particles, so it takes a lot of material to get them zero away. Most of the muons are absorbed in the dirt on the way to the SBND. And finally, we end up with a muon neutrino beam roughly peaking around 0.8 GeV. Some things sneak through, some of the muons get through, some of the neutrinos interact in the dirt, some extraneous neutrons. It's a lot of fun trying to sort this up with the data. You never get a pure beam. Most of the beam is muon neutrinos. Antineutrinos, there's still some. And there's also, of course, some muon decay, you get electron neutrinos. Any questions so far? Hope I'm not, I didn't know what level or what audience would be here, so I hope this is not too, I hope I'm not assuming too much.
I think that most of them are graduate students.
Graduate students? Okay. Feel free to interrupt. Okay, here is the Booster Neutrino Beam hardware. This is the horn magnet here. It's, I don't know, it's only look at horn. Not exactly. Inside is the beryllium target, instrumentation, and this is outside of the beam line. It's highly radioactivated during beam running. You have all sorts of materials getting hot. So we have to do an access. It has to be cooled down for at least several days before people are allowed to go inside and work on it. Okay, now on to the next topic, the short baseline neutrino program at Fermilab. This is not just SBND. This is a set of 3 detectors, set at strategic locations. Let's see, neutrino target is here. You see SBND is the MD is near detector, or neutrino detectors, whichever you want. It's the closest, and so it gets the largest flux of neutrinos from the target. Further down the beam line is MicroBooNE. Yes, that's MicroBooNE. And then finally, ICARUS. So the idea is to study oscillations that occur. Very few oscillations occur at SBND because they're so close. They don't have time to change flavor. But by the time they get to ICARUS, it should be clear. Here's the order of appearance. MicroBooNE stopped data taking, I think it was 2021. ICARUS is going strong now. It's been running for three to 4 years of physics quality data taking. And SBND is about to come online. Look at this picture, because the diagram is hard to visualize where things are. So here's the target hall. Here's SBND. Here's MicroBooNE. And ICARUS. I don't know who did this photograph. It must be in a drawing, I assume. All right. A few more details. The idea was the SBN program would have basically close to identical technology, detector technology. These are time projection chambers, each one of them bathed in a liquid argon bath. There's some key differences between them, which I'll go over. Oh, sorry. Bringing up that they're very different masses. Argon has, ICARUS has to be huge because it's farther from the beam, the beam is very spread out. And to collect more neutrinos, it's bigger. It's like quite a bit bigger than the SBND. SBND is a little bit bigger than the MicroBooNE. It can start late. It has started later than ICARUS because you can accumulate huge numbers of neutrinos much quicker than ICARUS. Okay, unified technology, water technology. So basic idea behind liquid argon TPCs. TPCs is a fairly old technology, 50 or 60 years old. Several years ago, the main guy who invented the TPC technology, I can't remember his name, came to Fermilab to give a talk about TPCs. He got a desperate call on the phone from the CIA asking, how far into the future have you been able to get so far? Time projection chamber. But it really happened, so. Okay, I mentioned that the neutrinos is the probability of oscillation. At the SBND is very low. At ICARUS achieves a peak. This SBND is crucial for normalization, for things like cross-sections, and establishing if you do see something funny at ICARUS, which will rule out that it was also seen at SBND. Other fun things, SBND is a prism. You can see what the beam profile looks like here. Simulation. Every concentric circle has a differing neutrino energy spectrum. So if you know anything about nova, that's critical to their success. If you don't look at the beam here, but you look at off axis, you can improve the energy resolution of the neutrinos. Okay, this is one of the biggest motivators of SBN was the sterile neutrinos that was hinted from the MicroBooNE experiment. It's called the low energy excess. Could be explained by the existence of a fourth generation neutrino. This is a neutrino that does not obey the weak force. The only way it talks to other particles is by oscillating. Also, sort of non-sterile neutrinos oscillating to sterile and vice versa. Greatly, SBND will provide a huge number of order of magnitude more than neutrino tests than we have now. Just to summarize, sterile neutrino oscillation, neutrino, electron neutrino appearance and disappearance, and muon neutrino disappearance. And ask our colleague Ornella about beyond the standard model searches. And of course, regarding further cross sections, neutrinos and neutrons with liquid argon itself can be important for the Doom physics. Okay, I mentioned the low energy excess, and last year, MicroBooNE released their first look at the low energy excess search. This is reconstructed neutrino energy here, and using looking for a possible sterile neutrino using a model based on the observed low energy excess. Other ways to do this. This is what they did, and you can see the red dashed line here is what their MicroBooNE based model predicted if there were a sterile neutrino. I didn't phrase that right. This is what it would look like if the MicroBooNE results were consistent with the MicroBooNE results, saying nothing about whether there's a sterile neutrino directly. However, clearly it's not consistent with the MicroBooNE model, but it does not rule out the existence of a sterile neutrino. Going on to the other detector, ICARUS, had a grand voyage from Gran Sasso underneath the mountain there, and to Fermilab via CERN. It was extensive refurbishment at CERN, cleaning, tightening up the wires, alignment, and about 2020 things were wrapping up installation-wise, and March 21 we got a steady data taking. There's four TPCs, 2 in each module. There's one. If you notice that it looks like a shipping container, that's not a mistake. It was designed to be moved around between Gran Sasso and CERN and Fermilab. So, these TPC modules spent a long time in the summer outside in the hot Chicago sun.
Do you think that when they start to pack the place?
They had to put water sprinklers to keep them expanding too much out in the parking lot. But ICARUS is happily taking data. They have not. They have had a number of technical papers, but they have not released any physics papers. Not even any calibration papers. All right, ICARUS. More pictures of ICARUS. This is the last stage was a cosmic ray tender. This is. You'll see in a moment that pretty much every single event that you record in one of these detectors has multiple cosmic rays in them. You have to filter them out from your analysis and only look at the actual neutrino interactions. ICARUS is the manager can look at both the new beam and blue here and Booster Neutrino Beam here. Whereas SBND is so far off axis the new beam, you can see that there's nothing there. So. Okay, more details on the SBND detector. SBND was sold as a R&D project for the Doom fire detector, FD1. This is the first one that will be built there. You can see kind of a cool picture here. See the field gauge. See the wire bias, it's not very clear. So, tired here, sorry. So, here's an blown open display. You have it's basically almost a cube, not quite. The cathode plane, which provides the drift high voltage and sets up an electric field between the cathode itself and the anode wire planes here. Below this up looks very beautiful. There are 3D planes of crisscrossing sense wires. And for a while it was out on display at the D0 building, which Vinny knows well. And the coffee. Again, the field cage is shown here in the sort of slats. That's to step down the electric field evenly so we maintain the volume. It's almost a constant electric field. That's a major job to actually measure the electric field in 3 dimensions in this volume. Here we go, the light detection is behind the wires. Traditional PMTs coated with a TPP material to shift the light from the UV range to the visible. One thing I forgot to mention is that, I should have said this earlier, detection methods. So we have 2 things. We have liquid argon, neutrinos going into the liquid argon, interacting with it. And there's 2 detection mechanisms. There's a scintillation light and ionization charge. So we have electrons and photons that need to detect the anode wires here, detect the electrons. We'll explain more about that later. And the PMTs and the apresentarás here. Aforementioned apresentarás in the black and white, or not black and red. And PMTs in the big round spheres. Detector status, like this picture. You see inside TPC, you see anode wires here and here, and light detection behind them. So you have if you know anything about Fermilab, we constructed the SBND detector at D0 building. This is another Tevatron collider detector. It was moved in December 2022, which was another big event. And eventually, actually, this is last month, moved into the credit site. All right. Here's a summary of the detector systems plus the cryostat. This is the time rejection system chamber, photon detection system, which has photomultiplier tubes, and apresentarás with silicon photomultipliers. Like ICARUS, we have a cosmic ray detector. These are sheets of scintillator right out the systems. They are used to tag 2 reasons: to tag cosmics you want to get away, remove from neutrino events, and also between neutrino events you want to take calibration triggers. Here's the heart of our TPC. Basically, you're taking 3-dimensional pictures of charge tracks going through the liquid argon. You can see. So they create ionization tracks. There we go. There's 3 sets of planes. So we call the 2 induction planes. These are negatively charged wires that do not collect any drift electrons. They provide sort of overlapping stereoscopic view of the track, projection of the track, as you can see here. And finally, the farthest from the cathode is a collection plane. It's positively charged, so the wires do collect the drift electrons. See, as an induction plane, charged deposit looks like this. The electrons pass towards the negatively charged wire and then induce a charge and another charge as they pass the other side. I hope that makes sense. Okay, other interesting things. The cathode, the drift plane is running at minus 100,000 volts. Easily be fatal. So very safety concern around this power supply. The voltage is tuned to maximize both the drift electrons and the scintillation light within the drift distance. run plan. ICARUS has been collecting data for a while now. So running SBND will run until the accelerator long shutdown, 2027. This is for the PEP2, the LBNF, and the DIM lines will be installed at that time. So the nominal running period will be, well, okay. It's running October, it's like November 23rd. Again, the SBND is free to start out later since the neutrino rates are so much higher. There's some fun sample event displays machine simulation. You can see here, yeah, U.S.A. cascading down to protons. They have a stray cosmic track here, and another one over here. Just the filtered out. I think I got it completely here. Sorry. It's a much more complicated interaction. You have a proton, pi zero, which contains two gammas, a muon, another pi zero, re-interacting downstream. Okay, so that sort of concludes the introduction to SBND and the SBND program. Something that we've been working on is the data acquisition system. This is something remarkable about SBND compared to ICARUS or MicroBooNE is that the preamp and a digitizer here inside the cryostat attached to the TPC itself. So here is an example of the cold front-end motherboard. These connectors go onto the wires, connect very closely to them. You see digital signals coming out here and power going in here. So ICARUS does not have anything in the cold in the electronics. It does it entirely in the warm. MicroBooNE had a front-end preamps in the cold, but the digitization in the warm. So the question is, why do we do this? Reducing waste. So this is where it gets interesting for doing. Cryogenic temperature to reduce electronics noise significantly, although that does depend on the transistor technology, silicon technology that you choose. The digitization inside the detector occurs very near the wires, so there's much less chance for environmental noise pickup. And DUNE will be using this technique, so SBND are ready for DUNE. Here's what we call a cooldown curve. This is a temperature inside the cryostat as a function of time. As first the cooldown occurs, where liquid argon is dumped into the air, dripped into the cryostat. It evaporates immediately and brings down the temperature of the whole system. As sometimes it gets cold enough, it begins to fill with liquid argon. And curious thing to note is that the noise goes back up a little bit again. This turns out to be the fact that the liquid argon has slightly higher capacitance than gaseous. So it's good news that MicroBooNE exceeded expectations. We expect with cold digitization that SBND should do even better. TPC DAQs, more remarkable facts. We have 11,264 wire signals to digitize. Do it in a waveform or keeps changing about 3 milliseconds. 3 milliseconds of waveform occurring. If you know anything about cosmic rays, that's a lot of time for cosmic rays to pass through the detector. 88 cold motherboards attached to the TPC, a custom preamp, which shapes, filters, amplifies signals coming off the wheel. This is new compared to ProtoDIM. We have used commercial off-the-shelf APCs, which require an extensive testing and a testing program at cryogenic temperatures. Before you saw the back end, readout system. So this is the front end of the lower right. This is the back end, which stores and compresses and reads out the data and sends it, desynchronizes it and sends it to the server, the DAQ system. Part of the commercial off-the-shelf tests where we did a test of the SBND TPC readout system and the Larry detector and cryostat here at Fermilab testing again. This is the first charge particle tracks going through the Larry detector, but using the SBND readout. That's what I'm going to do. This volume here will all be filled with liquid argon. And there's the cold motherboard. SBND PDS light readout. This is for photomultiplier tubes and the hookah systems. Scale is 120 PMTs, 196 hookahs. We use a commercial product called a Kane 1730 digitizer. You can see it in red here. And we digitize at a rate of half a gigahertz, so you get a sample waveform every 2 milliseconds. There's no hardware compression, so counterintuitively, the PS data dominates the data acquisition system. And end up compressing in hardware. So we have other hardware. There's the high voltage signal decouplers. There's the high voltage power supply system. I forgot to include the upsides. Sorry. All right, we have taken beam data, but so far only with the Cosmic Curry Tiger. Again, these readout system uses SIPMs, readout simulator tiles. The SIPMs are integrated with the readout into one device on the order of 1 nanosecond time resolution. However, no waveforms, because that we would be overwhelmed with data. This is designed at the University of Bern and available commercially now. First used by MicroBooNE and ICARUS. You can see here, the important part here is that you look at hits from the CRT, the simulated metals, as a function of time relative to the pre-beam alert. And you see that, yes, in the expected beam window, there is an excess, a significant excess of hits. So you know that things are fairly well timed in and understood the first order. Here's Ebor's CRT readout boxes. There's some test paddles, the initial one, and the big paddles that cover the entire cryostat are in the process of being installed as we speak. And that sort of wraps it up for my SBD and SBN talk. Just a few comments about future neutrinos formula. Probably most of you have heard of the DUNE experiment and the LBNF long baseline neutrino facility. I hope this is a new beam line using the new beam again, but instead of sending the neutrinos to northern Minnesota, you send them to a facility, a former gold mine in South Dakota, which has the added benefit of being about a mile underground, so we get much less cosmic ray background. I guess SBND and ICARUS are very close to the surface, so that's why we have some cosmic ray background events. Here's this is not to scale, of course. LBNF, this is a quick diagram of the facility beam. It's initially designed for 1.2 megawatts of protons, easily upgradable to 2.4. It's sort of second phase. I'd like to mention this because I'm also working on proton improvement plan 2. I mentioned earlier the LINAC, which was the oldest accelerator in the Fermilab complex. It's time to retire it. It's brand new, superconducting RF cavity LINAC So we'll increase the power to at least 1.2. And again, have an easy path forward, even more power. Okay, any questions? I forgot to say before we go. Thank you for my collaborator and colleagues for input for these slides. Apologies for not being super alert.
Questions, preguntas?
I have one question. If you have a supernova, at the time the SBND is operating, can you detect the neutrinos from supernova from MD energy range?
Sorry, get closer.
Can you detect the neutrinos from supernova?
Yes. Oh, totally forgot to mention that.
Yeah, especially the radiation burst in the beginning.
Yes.
Because the MD energy range, can you see this so low energy?
SBND, not ICARUS, has a separate parallel data stream, which, because if you digitize every single crossing ever, every single tick, every single clock cycle, it's a huge tsunami of data.
Mm-hmm.
So they have a system of lossy compression. So the primary booster data acquisition stream has lossless compression, but the supernova has lossy. So we store that data stream for a few days or a week on local disks, and we wait for a snooze alert, and then we mine the data after the fact.
I see.
Because we don't have enough computing and electronics power to actually produce a trigger. That would be nice, but that's not in the cards for SBND. Maybe in the future.
On the slides, since I guess this is a related thing, on one of the slides you said that one can watch the formation of a black hole in real time. I guess you mean a flux of neutrinos which suddenly disappears or something like that.
That's it.
I see.
On the point of view of the particle that came from the target, what's the relativistic distance that the particle or the neutrinos fly? Because you have three detectors, 150, 40, 45 or 400 and 600. What's the distance on the point of view of the particle?
Point of an oscillation
Relativistic.
or relativistically? Well, with neutrinos, I mean, 0.8 GeV peak. So if it were a proton, that would not be so relativistic.
Just a little bit. The velocity is close to the light velocity. No?
It's basically.
Yeah, right. Or pretty close. Not exactly, but I guess the point of view of the particle, the relativistic distance is not one, for example, SBND is not 150. Okay, it's a little bit closer to the target. No?
It's close to seeing, yeah.
Yeah, to have an idea what was the distance that the particle see of the detector.
Can't do that in my head right now.
Okay. It's just a curiosity.
Remember, Minos measured the speed of the neutrino because, if you remember opera experiment, I think it was also a Grand
This
Cessna.
happened when the same time that opera gave that announcement about the velocity of neutrinos, right? Because I remember that the Minos was in that same time.
Yeah.
It
Well,
was,
the first one was ICARUS to measure.
and because he measured, he did the measurement.
Started
the
over
right
trouble.
guy.
If you remember, opera said, their measurement said that the neutrinos went faster than speed of light. But there was some problem with a cable or something.
Yeah,
so
exactly. Exactly. The problem is the tree. I'm curious.
The misconnection of the optical fibers along
Oh, right. Shows you the importance of everything in systematics. That was at the main auditorium in CERN when they did their initial announcement. The funniest part about that was, sort of in the balcony, a theorist raised his hand. He said, I wrote a paper 2 weeks ago predicting this exact result. 2 things you know you got it ahead of time, and 2, he was wrong.
No, instead in the Gran Sasso, the theorists say it's impossible because when the supernova, when the neutrinos from supernova right here in 1987, the difference of time between the arrived neutrinos and the light was something around 6 hours. And if that results from Doppler was really true, we should see a difference of time between years. But the problem is that in that moment, in the past, there was no detector for supernova that was running, and there was not to be able, we are not to be able to control theorist ideas. But of course, after his measurement,
My measure.
no, I would like only to give a comment for the people here that this technology that Bill is talking about, the Liquid Argon TPC, was invented by Carl Huber. That was a Nobel Prize. So in around 1978.
78.
Yes. And the first experiment that had been done using this technology was ICARUS, the same that he showed you, that now is in operation at Fermilab. But as you see, the ICARUS was moved from Italy, from Gran Sasso National Laboratory to Fermilab. So the first ICARUS had been built by the Carl Huber groups. And after he was working, he did his PhD, master in the time in ICARUS. So we see everything that's happening since the beginning. And then they moved this ICARUS to Fermilab after, in the middle, the ICARUS goes to serem to be refurbished, and then goes directly to Fermilab. And now ICARUS make part of this program that Bill tell us that is SBND program. So it's 3 detectors. So ICARUS, MicroBooNE is already working, ICARUS also, and now SBND, that is experiments that we are working here in Brazil in the laboratory labs. So if you can back for the slides that you showed the photon detector of
Which slides, sir?
the ones that you showed the photon detector of SBND. And the other. Yes. So see that this is the SBND detector, and we have almost 200 X-hookahs inside that make part of the formula. Half is to see UV light, that is the light produced by a scintillation photon inside the liquid argon TPC, and half is built by to see visible light. And why visible light if a liquid argon TPC is working in the regime of ultraviolet light? Because in the cathode there, we attach it in all cathode in both parts, foils with TPB, that is a converter. So basically when the event happens in the middle of between the cathode and anode, because of light isotropic, part of the light goes in the direction of the photon detector, and we will see the direct light that will be seen by apparatus for UV light, and part goes directly for the direction of cathode. And when arrived at the cathode, in the cathode there is these foils that can convert these photons for a visible photons, and again, when he emit, again isotropically, and part of these photons go back. So we have one more time to detect the photons. And all these particles have been built here at Unica for our group, based in the DRCC, the Venice, etc. And the foils with TPB also have been done. Part of the jet foils have been evaporated here in the laboratory reactors. And we have a hugely precise contribution in SBND, right, Bill? So Monica, Gabriela, so I think that more than 10 Vinicius, Cecilia. So I think that our group, that we have a huge contribution for this experiment. And our students are Luca and also Gabriel. No, you know, sorry, was lying. They already was there. But they spent some time at Fermilab working there. So this is an agreement between Fermilab and Unica. That if you are interested,
There's also multiple fellowship possibilities.
yes.
Intensity Frontier, Neutrino Physics Center,
Yes.
and Hope to Fade. It's mainly for young people, but I think it could be engaged.
Yeah, so this is an opportunity for the young people that wants to work in this area.
Pay a significant fraction of travel expenses, living expenses when you're there.
Further questions?
So SBND will work next year, so if you want to join our group,
It's a good time for a young person.
it's a good moment to enter the collaboration.
Huh? I'm here. You have a question? I'm here. Oh, yes. I actually have a short question that I didn't. I mean, you mentioned that the justification. Is there sort of a specific anomaly? I mean, I'm sort of an outsider to this, but is there a specific anomaly that motivates short baseline, or is it sort of a consistency check on other experiments?
Short baseline and long baseline cover different phase spaces and
Sure.
neutrino mixing angle. Somebody like, not a library.
Beyond standard model, right? So beyond the stellar.
There is some anomaly. Just this item, so if there is some anomaly that would justify the shortage.
Yeah.
This is the low energy excess.
Yeah, there are several anomalies that can come.
Yes, of course.
Yeah.
One historical anomaly that is LSND, which observed an excess, which is a shortage one experiment, it observed an excess of neutrino electron from a Beam from time to piece decay. And this corresponds to this baseline, more or less. To this, and then there was the mini-boon, which is the precursor of MicroBooNE, which is here. That again, that was built to clarify this anomaly, but observed a similar anomaly, but almost not so compatible with the SBND. And so this program is to more or less rule out all the phase oscillation parameters.
But this is specifically
This is my.
asking for short baseline.
Yes.
It's asking for rapid oscillation. Further questions? If not, thank you very much. That was, I know what it's like to spend the night on the plane and come here and like talk to people.
Easy.
But we will stay here for more 3 days, so if you want to have some meeting, we will be in the you can
Muito obrigado.